Hi, welcome to another video. This one's sort of culmination of a couple of the projects I've done. This is a GLCD clock set up as analog format, as you can see there, but every quarter past and quarter to you'll see the regular time comes up. It's an MSF receiver, so I know this is synchronized. Right, every 4 minutes the PIC controlled clock there turns this board on, turns the power on through a pass transistor, drops the voltage to 3.3 volts via this regulator here, gives us 3.3 volts on this PIC microcontroller, which benefits this transceiver because they're meant to run on 3 volts and not 5. This is the like the Nordic NRF24 L01 transceiver. They're a half duplex, so you can't transmit and receive at the same time. You enable one pin to transmit, enable another pin to receive. So what happens with this one, this powers up, 15 seconds later I get another signal from the clock. It turns this transistor on, which grounds this pin, which you'll see the source code later, or it's all on Microelectronica's website for their source code for the Nordic transceivers. It grounds this pin, which enables the transmitter, and then for my other project you'll see here I've got the Linear Technologies current sense amplifier. I've calibrated it with a couple of half ohm resistor to 1 ohms in parallel. This turns on, so 3.3 volts to here, ground, and the output, this yellow wire, runs to A0, which is the first analog to digital converter channel, port A. It's actually pin 2 there, but so there's my current sense amplifier. That measures the current coming off my solar panel, sends the voltage out here. So if we got 3 amps through here, I'll have 3 volts coming off the yellow line, 3 volts going into the PIC microcontroller, and because the whole lot's running at 3.3 and not 5, I'll have better resolution. So 3 amps will give me 3 volts, which is just under 1023, 1024 bits. So having a 3.3 volt regulator benefits the Nordic transceiver. They're meant to run at 3 and not 6. What then happens is once this has sampled the voltage, it's sent to the UART terminal internally. That transmits the voltage via UART and this transceiver, and then I can pick up the voltage downstairs. Right, so as I say, these are the Nordic transceivers, half duplex. This is off eBay. I think I paid about £1 plus maybe 50p shipping. Well, get onto Microelectronica's site, look for their NRF click. So that's their click module, just plugs into the board. But as you see, I'm not using their modules, I'm using some of my own. I just happen to have them in the drawer actually from over a year ago, never got around to using them. Right, so what I've done is taken the NRF24 transceiver, taken it off the experimenter board, put it on its own single board down here. So this is receiving the data, and this PIC is purely converting it to UART. So I've got power on this board, and I don't know if you can see over the back, just 2 wires for the UART running up to my EasyPIC Fusion version 7. Now what I've done, I'll show you the code, but so what I'm doing is simply getting one of the NRF transceivers. One's transmitting the data upstairs, you saw in the earlier clip. That's transmitting the data, this one's receiving it, and I'm reproducing a string down here. So this is the string being transmitted from upstairs, and these are parts of the string, or the relevant parts. It's the actual data being transmitted. So this 208 divided by 33 gives me my solar panel charging current. Right, we'll wait for the next bit of data to come in. There we go. So that's the string of the data. It's actually cut down in length, and that's the relevant data we want, the 186. So 186 divided by 33 will give me my charging current in hundreds of milliamps. So if I put that on the calculator, 186 divided by 33 equals 563 milliamps. And what that will do, I'll show the code as I say, that 560 milliamps, I'm actually dividing it by 10, so that will actually be 18.6. The 6 won't get written to the EEPROM memory. Don't know if you're aware that EEPROM 128 bytes of data, you can't start storing floats, that sort of stuff, so I'm missing some of the data, but I'm capturing the sort of most significant part. There's a little EEPROM up there. We'll wait for the next bit, then I'll show you some code. I'm not sure if it's these NRF transceivers. These are just sort of cheap ones off eBay, but every now and again it will drop one of the bits of data and I'll get errors on the screen. Well, you can see this, so it's obviously 17:25 in the day, Sunday. There's normal clock routine, and then the UART interrupts the clock, gives me this string. So if the sun's going down, and you can see that it's 160 now, so 160 divided by 33 equals, that's down to 484 milliamps. Right, so this is Microelectronica's Micro C Pro for PIC32. The program I'm actually using, you can use with a sort of the earlier 16 series chips. Doesn't have to be a 32-bit. Just put the data on a monochrome screen if you want. So this is the basics. You can get all these samples or examples from Microelectronica. So this is just writing to the external EEPROM. And I've just changed they were shorts. Just changed them from shorts to char, so address and data, onside char, address 1. That's what we're doing, writing, or how we write to the external EEPROM. Now I'll scroll down to the other bits. This is the important bit, so these are the chars and ints for the string we're going to pick up from the UART. So you see the main data is coming in, and I've called it NRF data, and I've assigned 100 characters to it, or 100 lines. J is just a counter. The string that comes in is called a string, and that's the little asterisk points to this string. The X is just for the EEPROM. So the char receive, I know my string is, I think it's about 29 characters long, but I've just assigned 30 spaces for that receive text, or this is converting it from an int to a string. Onside short for the ready, which I'll show you in a minute. Right, so this is actually the interrupt, but little tip, this is actually the proper true interrupt down here. And what they recommend, because of addresses in the chip, you don't start fitting loads of code in here, because A, it will overwrite other registers, and B, it will take too long. So you need to grab the interrupt and then disappear, just to keep this interrupt short and tight. So when a UART interrupt comes along, it just simply goes to UART handler. I called it UART handler, which is immediately above. So the UART handler, make sure you're on the screen there. So when the data comes in, I'm simply calling the string, so NRF data J equals UART to read. So a string comes in, that's my 30 bits in the string, is called NRF data J. when it's got one string and the next string comes along, this starts incrementing. So it's like NRF data 1, NRF data 2, NRF data 3, keeps on counting up. So that's J++, and then if J equals 100, ready equals 1, and then I clear the UART2 interrupt flag. I clear the flag in the handler. So this ready equals 1. So you might have seen in various examples this is ready for passing. So I looked up the term because, to be honest, I wasn't familiar with it. In computer language, I'll just scroll along here, it's from Wikipedia. It's a term used to refer to the formal analysis by a computer of a sentence or other string of words into its constituents. So there you go. Right, so we've got our string, goes to ready, so mess all this is all the clock. So while 1, so just let me show you all a loop. So you saw if our string's ready, ready equals 1, so for the time my clock, if ready is not equal to 1, get the time and then show the time. So we don't interrupt our UART coming in. Right, so this is the overrun buffer. Just keep that on there all the time. So if you get overrun errors, it's going to automatically clear it, and frame errors, if you get errors in the frame of the UART, it's going to clear it. Right, so this is if ready equals 1. This is similar to the GPS example on the monochrome screen they've got. So ready equals 1, you're clearing the ready flag. This was just turning on an LED, just I could see if I had got to this stage, I'll turn on an LED. The string is equal to the string. Have a look in the examples of the library manager to get the definition of this. It's looking for the string and the first occurrence of this pipe. Now on microelectronic is an example of the NRF. It transmits pipe before anything else. That's the start of the sentence. So much the same way as my earlier GPS video, put the start of the sentence there, and we're away. If the string doesn't equal 0, which means if it's got this pipe, my receive string is equal to, move you over a bit, so receive equals, so I'm looking at the 25th part, 26, 27, 28. So those 4 bits of the string are the bits of data I need. So what I've actually, it's a long story, but I'm saying when this happens, old state increases by 1, and that's because depending on the length of the string, you'll get your UART interrupt, it'll start running down here, but then you'll get, if the string's too long, it will happen again. So I want to capture the first part of the data. You don't need this old state. But so if you have got this old state, during the first bit of data, the receive 1 equals receive, which is our string up here. Then into string receive 1, receive text. Then obviously that's the font I'm using, and then I'm plotting the received text on the screen. If you could write the whole string, but you'll get 3 or 4 strings depending on how big the font is. But what I'm using here, I'm using strncpy command, which cuts the string down to 29 places. And then this is my EEPROM address. It's just counting every time this happens, counts 1 EEPROM address and writes the receive value divided by 10, writes it to the EEPROM, and then I can read it later. And then I'm turning the LED back off. I had trouble, these LEDs, I had trouble, I was reading the string, but it wasn't being processed. So this is why I put an LED on here, and off at the bottom. So if my LED lit up, I knew ready was equal to 1, but I wasn't getting this bit here because the LED wasn't turning off. So if you're having trouble with strings, your little, well, it's a tip, but put an LED on somewhere, and if it lights up, you know you've got to hear. If I had like a typing error here, or the sentence didn't begin with a pipe, my LED would turn on and it wouldn't turn off because it would never get to here. The string would never be equal to pipe. Well, just before I show you the UART on the PC, you can see my last bit of data, 35. So 35 divided by 33 is sort of just over 1, so I know my charging current's down to just over 100 milliamps. Oh, it's gone up again, gone up a bit to 37. But so I know 33 equals 100 milliamps. Right, what I've done, set this into a loopback, so whatever comes in is going to come back out on a UART terminal. You can see this little backslash and asterisk. I've removed this other statement, ready for passing, that sort of stuff. Removed all that because you can't have a loopback and do this at the same time. So I've already connected it up, set up the UART terminal. For those of you who haven't seen my other videos, got their tools, UART terminal. And you see the data coming in down there. So let me come off here, see if we can get a close up of this. Well, if I clear this, you can see the sun has gone right down, and look, my data from upstairs 18. So if I clear this, remember the data comes in every minute. You can add a time up here. You can choose a line feed or just across the page, and then carriage return, and carriage return, line feed, and line feed, and just carriage return. So while we're waiting for the data, so I've got a COM4 9600, one stop bit, no parity, 8 data bits, buffer size is 124, 1024, flow control none. Right, so you see the actual string coming in. There we go. I've got the time, let me take out the time, and we'll start getting strings across the screen. So this is a string there. It begins with pipe, those are spaces, pipe 32, this is channel, ADC data, 0008, so you see the charge codes come right down. And with these spaces, I'm picking up these 4 bits of data, which was it 29, 28, 27, 26, including the spaces. But when you use that command down at the bottom of the screen, let me scroll down, move this out of the way. When you use that command there, the string CPY, that removes the spaces for you, so you don't get the string or the spaces on the screen. But there we are, there's more data coming in. So that's transmitting every minute. I get about, I think it's 40, 50 strings every time. If the J value in your loop isn't big enough, you'll start getting this data coming in, and then the buffer will overrun and start causing the thing to halt. That's about it. Hopefully it makes sense. We'll clear this and wait for the last bit. So I won't touch anything. You'll see the first start of the sensors will be pipe. Two seconds. There we go. And now you can see it was down to 1, which I think that's a small error on my current amplifier. You get a 1 when there's no data. What I did notice, well, I don't know if it's these cheap NRF transceivers off eBay, when I do get data, sort of I'm maybe 300, 400 or 500, every now and again I'll get a 2. there's a 2 there in all of these ones. That 2 seems that it drops the data and just gives you a random 2. So my code's not perfect. I haven't sussed out how to actually ensure I only get the first bit of data and not the last, that sort of stuff. I'm working at the moment trying to write to microchips, one of their bigger external EEPROMs. This has got something like 16,000 bits of data, but it wants 2 numbers for an address, so I haven't figured that out yet. Well, so that's it. The sun's gone down. 17:50 Sunday, 9th of March, and you see that data being represented there, as you can't see it there because I've removed it from the clock, so there's no data coming to the clock. Well, this is a quick program I put together. So remember, I'm dividing the data by 10 so it fits in the EEPROM. You can't have numbers over 255 in a byte. So you see these are the values coming in. When you see a 0, you'll get a tall line, so that 0 is where the transceivers have dropped a bit. You can see it earlier on, that's sort of 2 hours ago, had rather a lot of them. So this is, remember it's divided by 10, so that 40 would have been 400, 380, so 400, so something like you're going on for an amp or something like that. As I say, forget these tall lines, but the actual data, you see I've got obviously some work to do to get rid of this. If you've got some advice, I'd welcome it. But you can get the trend of what's happening with the solar panel, and obviously I've only got 128 bits available on this EEPROM, so I only get 128 bits of data, which is why I'm trying to work on another EEPROM to get 720 bits, which will give me 720 minutes. So you can see the sun was coming up, the solar panel output current was increasing, and that's where I'm messing about with the program. I stopped it just now, and it's obviously started to drop right down. But yeah, these are errors, but it doesn't matter, you still get the trend of the current going up, which is good. If I left it on long enough now, this will obviously come down to nothing. Yeah, got to work out why those transceivers drop bits of data, give me errors. I don't know if it's timing. I've copied Microelectronica's software, just running on these standard PICs. 99% of data will be accurate, but just one bit of data might be wrong, and it's that one wrong piece of data I seem to be picking up in my string, and it's obviously being recorded there. If I knew how to get rid of that, I'd be a happy man. But yeah, so transmit your data, receive it somewhere else in the house, and obviously that's what I want to do, just plot the trend at the end of the day. I think I might be able to fit this program, this like 8-bit software onto this 32, but I've then got to tie that in with my clock, which is obviously running at a different frequency, and then the UART interrupts. It might start interrupting the transmission bits on this, which is fairly sensitive, the timing of the transmitter and receiver. It's got to be right to be paired correctly, so I don't know, maybe I'll come back to it, but it's not too bad. It gives me the general idea. Once I've got a day's worth of data, it'll obviously look better. And it's obviously, now we're coming into the summer, or we've had a bright day today, you can see it there. Anyway, hope this has helped. Might find it interesting. Thank you very much.